So thank you very much for this opportunity. So I'm going to present the results of our monitoring the air pollution near the schools in Warsaw as a part of this CoMobility project. And this is mainly the contribution of the, not mainly, is one of parts of that NILU, Norwegian Climate and Environment Institute in this project as a partner. And so I will present this, but my colleague Nuria as well, I don't know if she's in the meeting or not, is part of this work. This is part of the work package 6 of this project, I don't know. And it's about assessment of the benefits in the environment of new mobility patterns. This is the, as I mentioned, this presentation is mostly about monitoring air pollution. By air pollution, particularly, I mean here particulate matter and NO2 near the three, or we call them city labs, the 3 schools in Warsaw. Almost for 1.5 years, the data has been recorded. So I will go into the details later, but first I thought maybe I start the, I don't know exactly who are my audience. So I thought maybe I say a few words about the basic terms that I will use in my presentation, but you may know them already, and it's boring for you. So I start with this particulate matter. When we say particulate matter, we are talking about the very, very tiny particles suspended in the air. And depending on the size, they get different names. For example, we have PM, or particulate matter smaller than 1 micrometer, called PM1. But the most common terms are PM2.5 and PM10, which are the most pollutants, most important pollutants globally. And by PM10, we mean particulate matter is smaller than 10 micrometer, or PM2.5 is smaller than 2.5. And these particulate matters, they have different resources, or the different sources to different sources, not resource, different sources for emission. Usually they are from industrial emissions, or also from combustion of the fossil fuel, especially in Poland, as I know, the fossil fuel and burning coal is one of the major sources of PM emission. And also the dust emitted from the ground or the land also can be, I mean, as a result of wind, or we call them wind-blown dust emission, is also another reason. Well, also wildfire recently, because of the rising temperatures, also is another source of PM. And this particulate matter can have very substantial negative impacts on the health, especially when it's long-term exposure, and both for adults, but children are more vulnerable. Maybe the previous presentation was more relevant, but yeah, this particulate matter is particularly concerned for the kids and also for the older people in big cities. And I think in Europe, Poland is one of the hottest spots of this PM emission. I mean, in for example, in Scandinavia, we have less this problem, but yeah, Poland and generally east of Europe, it's more important. So yeah, this slide is a general introduction to noise pollution, but I think with the previous presentation, there is not that much to say. So just I wanted to highlight the effect of noise pollution and what are the sources in urban environment, like traffic, construction sites, or outdoor events or industrial activities. And the major cause is usually the traffic for the noise pollution. So yeah, also a small introduction about the low-cost air pollution sensors, or low-cost technologies for measuring the air pollution. Now, traditionally, the air pollution is measured by the official stations, usually monitored by the governments or by the environmental institutes. And the problem with these stations are they are super expensive to run or to be calibrated through all the year. And this causes that the number of the stations we have in urban environment is not enough to monitor all the air pollution locations and to find all the hottest spots. And for example, in this case, we are going to monitor the air pollution near the schools, and we don't have an official station near schools. I mean, the nearest is like 2 kilometers from the schools. And another solution is using low-cost air pollution technology, air pollution monitoring technologies, or I call them low-cost technologies. And they have become popular in the past decade, and we use a set of sensors to measure the air pollution instead of the official station. And here, for example, this big box is the official station that I was talking about. As I said, it's very expensive, but the data are officially released, and that's used for regulation. But we have these sensors here, these 3 sensors. They are much more cheaper, and still there's debate by cheap. I mean, here we have like 200 euros to 300 euros or even less. But yeah, we have 3 sensors here, for example, and can compare how smaller they are compared in relative to the station. But the good point or the good news is these sensors, these small sensors, because they are so small, they can be in mobile mode, or whereby the citizens or people, or they can be mounted on the bikes or the cars or the public transport vehicles. And also, even if they are in the static mode, because they are very small and compact, and they can be produced in large number and installed at different locations. So the gain here is that we get more data from these sensors, from a more temporal and spatial resolution from the sensors. But the problem with these sensors, because they are low cost and they are not regularly calibrated like the monitoring stations or official stations. We have local sensors. It gives us higher spatial temporal resolution. They are cheaper, but this comes at the cost of lower accuracy and maintenance costs. But compared to the official stations, the maintenance cost is much more lower. So yeah, we talked about those pollution, PM pollution, and the sensors, local sensors for monitoring the air pollution. So here, the aim was to evaluate the effect of local traffic on air quality and noise levels nearby the 3 schools in Warsaw. I will show you the schools here. We have the 3 schools of the Kajki, Troka, and the other one I could never pronounce, Kropskiego. And we had 6 early sensors. By early sensor, I mean these are the air pollution sensors. These are the developed and manufactured by the early company in Poland, and we purchased 6 early sensors from them to do this analysis to monitor the air pollution. And at the same time, we had 3 SONET noise sensors, which you can see here on the top right. And these were used for monitoring the noise near the schools. And these are from the Swantech company. And the diffusive samplers, I will discuss them later, but these are also another technique for measuring air pollution we have used in this study. I will discuss them later, but at the moment, just you can see here, we have the 3 schools and the locations of the air pollution sensors, the noise sensors, which are shown by diamond, and we have the diffusive samplers. For each school, we have 5 of them. And you see, for example, in Kajki, we have these KA0. These are the yellow is the diffusive samplers or passive samplers, they call them. So the difference between this sensor and the passive sampler is like a small package that we put there, and there is something like a material that absorbs the air pollution, and especially here we focused on NO2, which is usually emitted by the cars nearby the schools, and it's traffic induced. So this material absorbs the gas, and after like a certain period, like 1 month, 2 months, this sample can go to the lab, and there it can be analyzed to see what's the concentration of the pollutant. By pollutant, I mean NO2 in that location during that period. So they used a passive sampling technique. And we have this blue, these are the early sensors or the local sensors we discussed earlier. And we have these SWANET or noise sensors, the diamonds you see here at each school. So you see the sensors are located, one in front of the school near the traffic, the other one is the background or the backyard where we have less exposure to traffic. So the aim was to compare also what's the effect of traffic on the air quality near the schools. And the passive samplers, because they are more accurate approach or much more accurate approach compared to sensors, they are also close to this, at least one is close to the local sensors to evaluate their quality as later. And this is these two figures, they show the data coverage by each sensor, by each SWANTEG or SWANET sensor, and by the early sensors. Yeah, this slides now show the results of the air pollution monitoring. So I'm particularly talking about the PM 2.5 near the school. So as I mentioned, we have the backyard and we have the next to traffic sensors. And this is the background or reference background. By reference background, we mean the stations, they are officially monitored by the government. And here on this plot, there are like 1, 2, 3, or 7 of them we have here, but not all of them are used in our analysis because some of them are traffic stations and they are affected by traffic. So I removed the traffic stations, only the background station. But background in air quality jargon means the stations that are designed to not be affected by the traffic or other parameters that affect the air. This is somehow regional air pollution in a location and represents something that's not affected by the other sources, is only the larger scale pollution. And this yellow is the background. This is PM 2.5. This is the background. You see the sensors measure very close to the referenced monitoring station average. And this is also for the PM10, the value. So it shows the backyard against the traffic. So in the air pollution literature, it is widely accepted that PM 2.5 is not that much affected by traffic. As we see here, for example, that the backyard and next to traffic stations are more or less very similar. So it shows that both sensors in the backyard and the next to traffic are measuring almost the same, and it's very close, same value, and it's very close also to the monitoring stations, official monitoring station. And this is for PM10. PM10 is more, more emitted as a result of traffic. It's accepted that. But for example, for for the first school, I call it Crocs. It's more affected by the traffic because we have two major roads near the school, but for the two schools is not that much affected. The backyard, or maybe for the Kaiki is the same. But the point is here in March 2022, we have a jump in the values. And when I analyze this is probably because of a dust emission from Sahara, which affected the whole Europe in March 2022. So these are not outliers. This is the results of a huge dust emission event happened in March 2022. So this figure shows the diurnal or daily variations of the PM 2.5 and PM10 near the schools. So it shows that the values are averaged over each hour. So the peak of the values are in the morning and in the afternoon between like 6 o'clock to 11, and the lowest value are during the noon. And the peak in the night probably is because of the heating activities by the households near the schools and the whole Warsaw. And I think this is in line with other monitoring campaigns in Warsaw that usually during the afternoon and during the night, because of people use the coal or fossil fuel for burning, for house heating, usually the levels of PM are higher. But one thing, for example, here again for PM10, this is not necessarily being close to traffic has higher air pollution. I mean, I think during the night, the values in the background is higher. And this figure and this table shows the accepted values for the PM2.5 and PM10. So, for example, for PM10, the limit is 20 microgram per cubic meter per day. This is the daily average. So above these values, these thresholds, for example, above setting for PM2.5 is not healthy. That's the threshold. And I found this from this Polish Chief Inspectorate for Environmental Protection. I mean, the WHO standards are a bit different. And this plot is the weekly variation. So I average the values of the PM2.5 and PM10 that we measured by the sensors for each week. And the values are very in line with the activities near the schools. When the schools are open, we have higher air pollution, and during the summer when we have less traffic and less heating activities or household heating activities, we have less air pollution. So the majority of the exceedance of the threshold limit happens in the week, for example, A to 15, and also weeks 45 to 54. And this is true almost for all the schools. And this is the monthly variation of the values for all the sensor. Again, you see here in the March, we have abnormal values because of the continental scale dust emission that I mentioned. This figure also, I mean, is the best. I like it. It shows exactly what's the relation between air temperature and the level of PM in Warsaw. So the lower the temperature, the higher the heating activities by the households, and the higher the fossil fuel burning or the solid fuel burning, and the highest level of the PM is when we have the lowest temperatures. So these are the 10-day running averages or rolling averages, and you see the most of the from October to like January, like 3 months, we have exceedance of the threshold. And also here for PM 2.5 also is the same. I mean, both values are very relevant to each other. And as I mentioned, we have diffusive samplers analysis near the school. So these values shown on each figure near each circle. Circle is the location of the diffusive sampler, and this is the average NO2 concentration in that location from 31st of October until 1st of December. And it's like 740 hours. And you see the Kaiki, because it's in the more residential area, has lower values, but in the city center, we have higher values close to the traffic. And also the diffusive samplers show when we are, for example, this one is inside the school. But when we are closer to traffic in general, I see the values are higher. That again highlights that the role of traffic on NO2 pollution. I mean, for this school also here is close to this road. The school is between, and the values, the highest values we see are in Troka and the Crops school. And yeah, and Kaiki generally less values. And again, here we have the NO2 limits. The good point is that for all schools, the NO2 levels are less than the threshold. And finally, the noise analysis, the noise level. As I said, we had 3 sensors. I mean, the figure here shows the distribution of the noise level measured by all sensors during this 1.5 years. And the color shows the hour of the day. I mean, the greener shows we are going toward the night. So here are the midnight hours, and this is the afternoon. And yeah, for both the schools in the city center, we have higher noise levels, but for Kaiki, again, it's a residential area, we have less values, and depending on the recommended levels, for example, WHO recommends 70 decibel, but for example, the European Union suggests 55 decibel. So according to European Union, all 3 schools are above the limit, but for the WHO, but they are very close to the threshold. And yeah, this is the weekly, diurnal, weekly, and monthly variations of the noise. Again, for example, during the summer, we see less noise, and during the weekends, we have less noise, and the majority of the noise is in the afternoon. So according to European Union, again, I'm stressed that we have high noise levels near the schools, which can negatively affect the health of the students. And yeah, this is the road ahead, and we have to evaluate the sensors performance against the diffusive samplers, and also we need to calibrate the sensors to make sure that these values that measured, as I mentioned, we have a bit uncertainty about the accuracy of the sensor measurements. So the way to make sure they are correct is to calibrate. But according to values we see here, for example, for PM 2.5, they are reliable. I mean, we see that they are very close to the trends that we get from official stations. Yeah, thank you.